So obviously compound interest is not our only application of exponential functions. So let's take a look at a few other applications. So Marty McFly and Doc need plutonium to create the 1.21 gigawatts necessary to power the DeLorean. So hopefully you've seen Back to the Future, otherwise that all went over your head. The half-life of plutonium is 24,000 years. If the original pellet was 0.5 kilograms, the amount left after T years is given by, and notice they've given me this function. And so half-life, because I want half of what is left over, this is my original amount. And we haven't talked about this yet, but really to write this equation, and it's not always a of t, sometimes it's c of t or whatever other function. This is the initial amount, which is why that 0.05 is where it is. This is 1 plus or minus the rate. So in this case, the rate is 50%. I'm losing 50%. So this was actually 1 minus 0.5, which also happens to be 0.5 or 1/2. And then up here would be obviously whatever our time is. And we've divided it by 24,000 because that is the half-life. So again, not necessary to know that, but good idea to kind of know where these functions came from. How much of the plutonium would be left 25 years in the future? So again, T is how many years, and we're saying 25 years in the future where Doc and Marty plan to go. So I'm going to be basically plugging in 25. So 0.5 times 0.5 to the 25 divided by 24,000. And again, I wouldn't get crazy. I would just do all of that in my calculator, because it's really easy if you try to not do it in your calculator and do just certain parts here and there to make a mistake or to write a rounded value down, and that's going to give you obviously a less precise answer. And so when I plug all of that in my calculator, I get 0.49963911161. Well, how much plutonium would be left? It started out at 0.5 kilograms, and it looks like most of it is left over. So I would say about 0.4996 kilograms would be left 25 years in the future. So here's another question, and you can see the only difference on this one is that we're dealing with a true natural exponential curve, whereas before it wasn't, our base was not e, our base was 1/2, which makes it a little different. But in this case, again, I just want you to be comfortable with where all of these values are coming from, and because eventually you're going to have to actually write these functions yourself. And so remember, even though they don't tell us that, I can tell that this is my initial amount. And remember, if I'm not sure, I can always take P of 0, which means after 0 hours has passed, and I would take 3,000 and then E to the 0.13 times 0, because T is 0, which means I'm taking e to the 0, and anything to the 0 power is 1, and I'm going to get 3,000 here. And that actually answered one of the questions, because it says find the initial number of bacteria. Now, did I need to do all of this work to find that? No, because I know what an exponential function looks like. Then the 0.13 is essentially the rate, because remember, it was PERT. Oops. R is the exponent, R and T are the exponent. And so the rate is 0.13 and the time is T. So now if they tell me to find P of 7 hours after I started, then I'm just going to write that same equation. My rate is 0.13, my time is 7. So I'm going to do the exact same thing I did before, replacing 0 with 7. And I find that after 7 hours, oops, not money, after 7 hours, the number of bacteria is 7452.97 if I round correctly, bacteria. So again, know how to use your calculator, because really a lot of this week you need to know how to plug things in your calculator correctly. Here's one for you to try on your own. The second one should be pretty straightforward. The first one, we'll see if you were paying attention to what we talked about a couple of slides ago, even though I didn't write it down. So press pause, try this question, and then press play to see how you did. So again, here I'm looking at an exponential function, and the difference here between this one and our last one is now our base is not e, our base is 1.04. And I'm looking at two questions. What was the population in 1990? Actually, three questions. What is the percent growth? Oops, let's pick a different color that's not so similar. What is the percent growth? And then, what is the population in 2015? So looking at our function, the population in 1990, which is when our function is beginning, because t is going to be the number of years since 1990, the population in 1990 had to be 6191, because that's the initial amount. That's where it goes in our function. Remember, we talked before about how our function is going to look like this. I think we used a of t before. It really doesn't matter what function it is. C1 plus or minus r to the t. And so in this case, C is 6191 when C is the initial amount. This should also help us answer what is the percent growth, because if I'm taking 1 plus or minus r, obviously I must have taken 1 plus 0.04, which means my percent growth was 4%. That's where that 0.4 came from. So those two questions are answered. According to the model, what is the population in 2015 means now I'm going to take P of t, or P of years since 1990 would be 25 years. So from 1990 to 2015 is 25 years. So I'm just going to plug 6191 times 1.04 to the 25, just like that, into my calculator. So times 1.04 to the 25, and I get 16504. And because we're talking about people here, then I'm going to just leave it just like that. And I would round up if I needed to.